Good morning, everyone. Welcome back to Orlando Math Learning Academy. It's been more than 2 months since the last time I made the video. I've been back from Vietnam for more than 2 weeks already, and now I have time to keep doing what we have left. And yeah, so I've been kind of busy lately, and I came back to Vietnam to prepare my marriage. Now I come back here again to keep doing the lecture video for you guys. Alright. I remember last time when we stopped at chapter 3.2, and we talked about transformation of function. Today we will jump to section 3.3, and we talk about a new kind of function we call the piecewise function. Okay, so let me put over here piecewise function. Okay, before we talk about this definition, what's meant by piecewise function, let's take a look at the function we already learned in the past. So over the past 2 chapters, we also review and we talk about some very basic function we already learned. For example, like linear function, or quadratic function, or radical function, or even irrational function. For example, here, let's take a look at the quadratic function I have here. The first function I have is negative x plus 2 square. Okay, and you know this is quadratic function because it's a second degree over here, and the domain of this function is defined on real number from negative infinity to positive infinity. And another function I want to take a look at is absolute function. Okay, and the absolute function, the range is from negative infinity to positive infinity. Hold on, let me turn it off. Okay, all right, I'm sorry. I try to turn off the internet. However, the range in this case is from 0 to positive infinity, and we have to include a 0. Okay, so far I have 2 functions over here when we already learned about that. And what I'm gonna do is I'm gonna use the bracket. Okay, I'm gonna use the bracket. I want to combine these 2 functions together. Okay, I want to combine these 2 functions together. Okay, let me write the domain of this. So the domain is negative infinity to positive infinity. It's also negative. It's from negative infinity to also positive infinity. Okay. So now I want to combine these 2 functions together. Okay, and I want to apply the restriction for each function. For example, the first function, I want to apply the restriction here, x less than negative 3, and over here I want the restriction is x greater than equal to negative 3. So by doing this, I have a new kind of function, and we call that piecewise function. Okay. So what is piecewise function? Let's talk about its definition. Okay, but based on this example, I can have a kind of overlook the idea what piecewise function look like. It's like a combination of function, right? Okay, let's talk about its definition officially. Okay, so the first one is definition. So I'm gonna put over here section 3.3. Okay, so piecewise function is I'm sorry, I have a sore throat, so I couldn't speak well today. Piecewise function is, first of all, is a function. But it's not just a function, it is a combination of more than one function. For example, I have here is two function. It's a combination of more than one function. Okay. Define more than one function. Define on a sequence of subdomain. Okay. I have to use this terminology because I cannot say that defines on a sequence of domain. Okay, because we don't really sometimes we don't need the piecewise function is not defined on the whole domain of each function inside. Okay. So each function inside the piecewise function is called subfunction. Okay, so in this case fx is a piecewise function. However, the function let me call it f1 and this is f2. f1x, f sub 1 of x is equal to negative x plus 2 square is called subfunction. We have subfunction here and we also have another subfunction here. Okay, so the domain of piecewise function is the subdomain. This is the intersection of subdomain intersection of subdomain of subfunction. Okay. So this is we call this is subdomain right here. Okay, we have subdomain. Why I call this a subdomain? Because it is a small interval of the original of the function. Okay, because it's a subinterval. This is also a subdomain. Okay, so I repeat it. Okay, so piecewise function is defined. The domain of piecewise function is defined on the sequence of subdomain, or the sequence, or I can say another way that defined on the sequence of the subinterval of the domain of the subfunction. Okay, so the domain of the subfunction here is negative infinity to positive infinity. However, is the piecewise function is not defined on negative infinity to positive infinity, but it's defined on the negative of the subdomain of negative infinity to positive infinity. In this case, is the interval from negative infinity to negative 3. Okay. Let me give you another example. The piecewise function that is a combination of more than 2. Okay. For example, over here I have x squared, and this one defined on the subdomain x less than negative 2. Okay. Or fx equal to 4, and this is defined on the subdomain between negative 2 less than x less than equal 3. Okay. And a third function I have is 4 over 3x if x greater than equal 3. So x less than negative 2, between negative 2 and 3, and greater than 3. these three intervals here we call a subinterval, or we can call it subdomains of each individual function here. Okay, and each function here we call that subfunction. Okay, we call subfunction. And this one here we call it subdomain or subinterval. Alright. So as long as you can combine more than one of the basic function you already learned, then we have something called a piecewise function. Okay. Okay. Now let's talk about the graph of the piecewise function. Graphing piecewise function. Okay. So when you graph any function, we have to consider the domains, right? It's the same as you graph piecewise function. You have to consider its domain. However, the domain of the piecewise function is a sequence of subdomain. Then we have to consider many domains, okay, of the subfunction. Okay, when we it means that we have to graph piece by pieces, and we apply the restriction for each pieces. Okay, as long as we apply the restriction for each pieces, then we have the graph of the whole piecewise function. Okay, let's go ahead and graph something. Let me see. Let's go ahead and graph this example right here. Okay, let's see. Let me draw the coordinate axis. So in this example, we need to apply two restrictions. We have to graph this function, the first subfunction, then we apply the restriction for the first subfunction, then we grab the second subfunction and apply this restriction for the second subfunction. Then we have the whole piecewise function graph. Okay. So let's grab the first one first. I'm going to use pencil because I'm going to apply the restriction, so maybe I have to delete the part that I don't need it, because over here I don't need from the whole infinite, negative infinity to positive infinity. We don't need the whole domain, we just need a part of it, which is the call. We need something called a scale, I already mentioned. Okay. Alright, so let's see. This is a negative. So I know that the graph will be upside down. Okay. And this is quadratic, so I know it will be parabola. Okay, and the vertex is at -2 and 0. Okay, so this is 1 here, 2, 1, -2. Okay, so the vertex is right here, and the axis of symmetry will be like this. Okay, let me fix this a little bit. Okay, good. So after I got an axis of symmetry, I need to just plug in the value. So let's say I plug in x equals 0, x equal to -2. How about x equal to -3? -3 plus 2 is -1. -1 squared is 1. So when x equal to -3, y equal to -1. So it's going to be right here. Okay. So we make a mirror point. So I have another point right here, and the parabola will be something like this, right? It will be something like this. Okay. Okay. Now let's apply the restriction. We want everything that less than -3. So -3 right here. So less than -3 will be from here to here only, right? And we have to use the circle because it's not included at -3. Okay. Now let's grab the second subfunction. Over here we have a -2, so we have the V shape of absolute function. Then move everything to the right 2 unit, 1 unit, 2 units. So it's gonna be like this, something like this, and something like this, right? And let's apply the restriction, and the restriction greater than -3, so it's going to be when x equal to -3 will be -3, -2, -5. Absolute will be 5, 1, 2, 3, 4, 5 will be like this. Okay. And I'm gonna use the dot because we included -3. So our graph could be like this. Okay. And this one go up like this. Okay. So the graph of, again, the graph of piecewise function, basically the graph of each subfunction applied on its own subdomain or applied on its own restriction. Okay. So usually what I'm going to do is when I grab the piecewise function, I just grab the regular function. Okay. Then I apply the restriction. Okay. Some of the instructor teach that you use one of the value in the subdomain in the restriction to get the point. Then you just trace the point to get the graph. But I think that's not a good idea to me because that is very kindergarten. So what we should do is, we in college, right? We need to learn a better way. We need to learn mathematics as adults. So as a mathematician, so what we do is we should graph the whole function, and afterward we apply the restriction. I think that would be the best idea. Okay. Let me see what we should talk about next in section 3.3. Okay, because 3.3 it's just talking about piecewise function. It's nothing else. The practice is, again, it's also about a piecewise function. Okay, there's some word application over here. Maybe I'm gonna go through one of them. Okay, so third part, modeling with piecewise function. Okay, so the problem I'm going to pick to do is, let me see, I think I'm going to do number 18 here on page number 18 on page 270. Okay. Okay, so right here. Okay. Let's read the problem together. A tour of Elvis Presley's Graceland in Memphis, Tennessee offers a single dawn ticket for $69 each. If a group of 15 or more plan to attend, then a group rate of $62 per a dawn ticket is offered. The pass gives the ticket holder access to Graceland Underground, a sale guide to Elvis's two-customer airplane, access to his automobile, a museum, and Fashion King and Hollywood exhibit. I mean, there's a bunch of information we don't really need. Okay, they want us to write a piecewise function that model the total cost for each done ticket. Okay, so how we do this? Okay, let's do a quick summary. Okay, what happened here? They offer single adult tickets for $69 for a person. Okay. If a group of 15 or more plan to attend, then a group rate is 62. So the price will be $60 per person if we have a group of 15 attendee, right? So person who attend called attendant. I'm sorry, attendant. Okay. If we have more than 15 attendant, or x is greater than equal to 15. Okay. And we want to get a piecewise function out of it for x done ticket. Okay. Okay. Hey. So we have two cases. The first case is $69 per person, and the second case is if x is greater than 15, there will be $62 per person. Okay. Okay. So how we do this? Okay. Then f(x), the first function, because of course it looks like this is a linear function. Of course, we already learned linear function. We learned how to model a linear function. $69 per person and $62 per person. That basically that is the rate of change, the slope. Okay. So $62 x. Okay. If x greater than equal 15, and $69 x if between 1 and 15. It cannot be 0 because 0 means 0 person. We don't do that. Okay. And we want to graph this. Okay. For part B, we want to graph this. Okay, so I just go ahead and sketch this really quick. So 15 over here. So 62. So the slope over here is bigger. The slope over here is smaller. It means the slope bigger. It means more slanted. So it's gonna be something like this. Let me see. And this is no y-intercept, so it must go through 0 here. Okay. So 62. Let's see. Should be like this, something like this. So 15 here, so 15 here, 62. So it's gonna be something like this. All right. Oh, I'm sorry, it's not. It must be something like this. Yeah. Because it's go through 0, so it must be something like this. So I use the dollar because I don't want to take that part. So it's going to be something like this. There you go. Okay. Greater than 15. Okay. And the slope here is 62. And the slope here is 69. It means it's going to be like this. Between 1. So 1 here. If x equal to 1, if x equal to will be 69, so this is 62 here. Okay. 62 here, 69. Let me call it over here. So it's gonna be like this. There you go. And this one we have to use the circle, and this one we have to use the dot. Okay. The graphs mean that when we have one person, the price is $69. So 1 point right here, and we have to include it because of the equal sign here. However, when x equal to 15, we have to include the dot for this branch of line, for this line, right? We cannot use this anymore because it's 15. The price is only $62 per ticket only. Okay. All right. Part C. Find and interpret C equal 24. C 24. It means that the cost for 24 person, the total cost for the group of 24 people to attend. So 24 people is greater than 15. So what we're going to do is just block ahead 62 times 24. I replace 24 with x. Then I got the answer. We get price. D part. C4. 4 is less than 15, so I have to use 69 because if it is just 4 people, then the price is still $69 per person. So 69 times 4 will be whatever it is. Okay. Label the point from part C and part D on the. So part E, label the points of part C and D. So after you got the value here, after you got a value here, this is pretty big value, so because 24, 15 here, 30, so 24 over here. I mean, my graph is not really correct because I can tell over here is that because increment is not scale. I didn't really scale. 24 could be something, give you the value here, something bigger than 69, of course, but I have something less than 69 because my graph is not scale. Okay, something over here. 69 times 4 times 9. 276 when x equal 4, x equal to 4 here, 1 2 3 4 here, then will be 276 here, $276 if we have a group of 4 and attend the events. Okay, and this is pretty big number, so my graph is not really good, but I mean, what else we could do over here? I mean, because it's not scale, so I mean, I don't want to scale it because the notebook over here. So if you have a graphic paper, you should be get it right. Okay. Okay, so that's the one of example. I give you to model the piecewise function. Before I stop the lecture video today, I just want to tell you that recently Valencia just switched to another textbook. Okay, Valencia College doesn't use this textbook anymore, but I think that I'm gonna just keep using this textbook and